It is 2026, and the first video I'm making this year is about spurious emissions again.
Oh, shit. Here we go again.
I hope that doesn't bode poorly for the remainder of this year, but a friend of the channel, the Smokin' Ape, made a reply, if you will, to his testing video that he did on the Baofeng Mini. I'm not going to rehash a ton of all the other stuff. I'm going to try to simplify it as much as possible to say that I have the Baofeng Minis. I have 3, and there are 7 or so total other radios that I have tested. Baofeng Minis owned by different people, purchased at different times, tested against extremely high-quality spectrum analyzers, and we found that every one of them was clean. However, the Smokin' Ape has his number. I don't know how many he has, and he tested them, and he believes that they are dirty, meaning they create spurious emissions. Now, if it was just that, I would have left it alone. The problem is that the title of this video is the claim that all Baofeng Minis are dirty. I was willing to chalk this up as maybe he got a couple of dirty ones, and then that was it. However, saying that all of them are dirty leads me to a problem I have sometimes with testing radio equipment, and it is the fact that when you watch us collectively, these ham radio YouTubers, we are telling you things based off of opinion, but sometimes we're telling you based off of some kind of a measured fact or something that we have determined through testing to be true or false. And if we are testing incorrectly, then we are giving either falsely correct answers or falsely false answers. Both ways are a problem because, one, we could be telling you to buy radios that are dirty, meaning they create spurious emissions and would violate FCC rules, or we are saying radios are dirty and they really aren't. And that could be harming companies that, while you may not like them, you may not like the radios or the company, is unfair to that company. And I don't want either one of those things to be true. I want truth to be true. I want things to comport to reality, and I want to measure that reality. In my last video, I reached out to Eric, the creator of the TinySA, and I asked him specifically based off of how I was doing my testing of handheld radios, what do I need to do? And he said emphatically, you need to have 10 to 20 dB of internal attenuation. Now, Ape called that an appeal to authority in his video.
And then he reached out to the group's IO for the TinySA, and he talked about how he directed his question to Eric. Eric is the inventor of the TinySA. Just want to say I've been a member of that group for more than 2 years. I've talked to Eric plenty of times. He's commented on my videos. Talking to the manufacturer or the designer or the inventor, it's awesome that we can do that in a community like that. But that's kind of like appealing to authority. Doesn't exactly mean that you're right. We'll talk about some of Eric's public comments.
An appeal to authority is a fallacy that's used for argumentative terms where you appeal to the idea of a common higher authority, and then that is good enough to stand on its own 2 legs. This is not an appeal to authority. Eric is the designer of this device. He knows how to use it correctly and how to get an accurate data set from your radio under test. He's telling everyone to use 10 to 20 dB of internal attenuation so that the mixer can get its 50 ohm impedance it's looking for the testing. When you don't give it that, you're allowing spurs to be measured on the screen, which is what you see in Ape's videos. And you see them on mine too, but here's the spoiler alert. I'm going to show you how to tell the difference between what's actually coming in from your radio or what's generated internally. There's a very easy way to do it. Mark Knight, KD7DTS from Soda Plus on YouTube, is here with me, and we're talking about the TinySA. We're trying to figure out how to differentiate between real signals and internally generated spurs. Is that a good way to characterize it, Mark?
Yeah, I think that's a good way to think about it.
Yeah, and so we came up with Mark came up with a little test. We took my TinySA and a couple of my Baofeng Minis, and we did 3 or 4 passes. And the first set of passes was 56 dB of external attenuation, and we changed the internal attenuation settings of the TinySA. And then we took all the TinySA internal attenuation off. We turned it off, set it to 0, and we added 70 dBs of external attenuation.
Okay, so here we are with the exact same setup and configuration that I had when we did the first video, which I'll link below for your entertainment. We have our tiny Baofeng Mini, whatever it's called. We have our big-ass attenuator, which is a 100-watt, 40 dB attenuator. And then we have a mini circuit's smaller attenuator for 30. This gives us 70 dBm of attenuation. And this is where everybody's like, oh, Ape, you're using too much attenuation. Now here's the settings for our internal attenuator, and it's set to auto. I'm going to set it to normal for 0. So this means it's turned off. We're not using it.
And Mark, you've already color-coded these numbers, so we're leading the witness a bit here, but maybe break down kind of what we saw, because I think this is kind of telling of things that are real, as in captured from the radio by the TinySA, and then fake numbers. And maybe you can talk a little bit about what the fake numbers mean.
Yeah. So there's two different places you can generally get harmonics or spurs when you're looking at a measurement. They can come from the radio, and that's what you want to see, or they can be generated internal to the TinySA. And that is what you don't want to see, because that's not really a radio signal.
That's not the result set we're looking for. Yeah.
So how do you tell those apart? If there's mixing between the radio signal and the internal electronics of the TinySA, then you can tell whether or not that's a spur from the TinySA by wiggling the oscillators in the TinySA. That's called spur removal.
And that's something that the TinySA is doing when spur removal is turned on or off or whatever. Is that correct?
Yeah, so if spur removal is turned on, the TinySA is actively doing that check for you. What it doesn't catch is if you're generating harmonics within the TinySA itself.
Now, and also, you should note, the spur removal does not work past a certain frequency set, as per Eric, the creator, right?
That's right. It's generally for the lower frequencies, a couple hundred megahertz. But you start getting into the hundreds, multiple hundreds, 300, 400, 500 megahertz and above, and that technique doesn't work as well. And so it can leave spurs that otherwise you would catch. And it's worth noting, this is a TinySA technique. The big industrial strength spectrum analyzers, they don't need to do this. If you do see a spur, then the question is it from inside the TinySA or is it coming from the radio? And one way to check that, and the way that Eric recommends, is to adjust the internal attenuation and see if the attenuation of the harmonic changes relative to the carrier. So that gives you a number called dBc, or the attenuation relative to carrier.
Okay.
So in your harmonic mode, that's what you're measuring, is dBc.
And we are looking for what specifically? If it's a real number, they're going to kind of stay the same. And if it's not, if it's a spur that's being generated within the TinySA or something, then it will fluctuate greatly.
Exactly right.
Okay.
And the reason is that harmonic generation is a nonlinear process.
Okay, explain that, break that down, because we got a lot of non-engineers in the room.
It means that if you have half of the power, you'll get less than half of the harmonic generation. If the signal's coming from the radio, then the ratio between the fundamental signal that you want and those spurs, that ratio will stay the same. So the radio is staying exactly the same. You're adding a linear attenuator, and you would see both of those peaks just go and drop down a little bit. Mm-hmm. And then numerically, you know how much attenuation you added, and you can put them back, and you can say, okay, the ratio is exactly the same. So that's the ideal case where you're characterizing something real from the radio. If you're not, then you've got mixing happening inside the TinySA. So if you attenuate the signal further, you'll reduce the amount of harmonic generation. So what you should see is as you increase the internal attenuation, you would see the dBc number shift for the internally generated spur from the TinySA.
The fundamental frequency is the 1T at 5 watts transmitter. We saw that when we had the 56 dB, and we played with the internal attenuation numbers from 14 and 20 and 16. We saw it was relatively flat, meaning 37 turns into about 5 watts of the output, and you've got about a dB of margin, right, in our testing here.
That's right. Claiming any accuracy to within better than a dB with a test set like this is going to be a bit of a challenge.
Right.
So within margin, this radio is doing exactly what we expected at the fundamental.
And we saw, now just sticking with the 56 dB external, we saw that the second harmonic, hey, look at that, it followed pretty true as well, 69.7 through -71, -70.9. So it's tracking, right? It's just kind of like moving along. We let the TinySA handle it. But then kind of after that second harmonic, it looks like all bets are off. The third harmonic through the 8th harmonic, which is way up into the gigahertz space, you can see a lot of variation. And for everybody watching, those blanks mean that the spur completely disappeared. It wasn't there. On one test it was, on another test it wasn't. And so what do we take from the area in pink there, Mark?
The area in pink is showing wild fluctuations between these movements. That's an internally generated spur, and you're seeing amplitude variations or disappearances completely. And that says, look, the spur removal tool isn't catching it because these are frequencies that are above what the spur removal tool can handle.
Right.
But by applying a little bit of science here, we can tell these aren't real measurements.
And what is the science? It's that there's just a large variation in the numbers. But let's cut over to, we got rid of internal attenuation completely, set it to 0, and the external was set to 70. So I added 20 dB or added 14 dB on top of what the first test was. You see, though, that second harmonic, real harmonic, it's still negative 68.1. So it's tracking, right? They're within the same space. But then when you get down to 5, 6, 7, and 8, well, I mean, now you've got, first of all, you've got some signals that were never there before. So the sixth harmonic. And then between all the other times they show up, they have wildly different numbers too. So those are not real spurs. They're not being transmitted by the radio is kind of the takeaway.
They're not being transmitted by the radio. They are spurs. I mean, there's probably power there within the TinySA, or it wouldn't be reporting it.
Right.
But it's not coming from the radio.
And so using it as a part of a test set on if we're determining if a radio is clean or not is probably not an accurate way of coming to a conclusion.
Probably not. But we didn't trust the TinySA with one radio, one TinySA.
Right. It's a smell test. I think a lot of times we use it because it's very convenient, but we used a My Service Monitor, and of course we used the really nice SA from Doug, and our 7 TinySA or Baofengs that we tested, and we came to a very similar result with regards to data of the real harmonics the radio is putting out.
And so what we're doing with this TinySA is we're doing extra measurements to make sure that we understand what we're seeing. And if you have a bigger system, you just don't need to do that.
So when it comes to determining between real numbers that the radio is putting out that we need for our data set to determine if it's a valid, clean radio or not, versus these other pink numbers, what does Eric say about that as far as how to use the tool?
You need to check if what you're seeing on the screen is real. So he says to add a little bit of external attenuation. So on his spur-free dynamic range wiki page, which is a great reference where he shows screenshots of how to do this, he says you add a little of attenuation. In his case, he adds 4 dB of internal attenuation, and then he checks to see if the harmonic level moves down. If it moves down, then it was internally generated. So that's the key. You need to understand how to add some internal attenuation, check the dBc, and make sure it's not shifted.
He generally says you need to have somewhere between 10 and 20 dB of internal attenuation with the TinySA. But then what is the factor of external if that plays into it at all?
The external attenuation is to get you to the point where you can use only 10 to 20 dB of internal attenuation.
Ah, I see. So when we set external to 56 dB, it was so that we could play around with the internal attenuation. And
exactly. So
if
you have
the spurs are being generated inside the TinySA, adjusting your attenuation up or down internally will change the numbers, which is what we're seeing.
That's exactly right.
Aha.
And if you had a more powerful radio, then you would just use more external attenuation.
Yes, and I guess you could see that here because although 14, 20, and 16 are kind of intermingled, we took these numbers exactly in the order we did the test. But you can see that on that fifth harmonic, when we had 14 dB, it was at negative 79.8, and then we went to 20, which got rid of it completely. Then we went to 16, and now it's 76.3. God, it almost makes you think that just the way to use this tool is to just always set internal dB to just always set it to 20 dB internal.
Well, I actually have a recommendation for that.
Oh, okay. What is it?
So if you have a 5-watt radio, and that's mostly what people are testing, you want to use 100 kilohertz RBW.
Yep.
That's the recommended bandwidth to give you a good low noise floor and for the spur removal tool to work.
Okay. Yeah. 100. So
that's going to get
when
rid of
you're
the
setting
internal
up
spurs.
the harmonics monitoring kind of thing.
That's right.
Yeah.
So spur removal on, 100 hertz RBW, and then 50 dB external attenuation and 10 dB internal attenuation.
10 dB, not 20, because we're seeing from our numbers here that 20 dB seems to suppress a lot of those fake numbers.
It does, but you're also reducing the signal level that the TinySA has to work with. So if you start with 10, that's the the TinySA creators recommended minimum internal attenuation.
Okay. Yep.
And that gives you 50 dB input impedance. So it's going to match to the radio. If you're using less than 10 dB, you don't have a 50 ohm port on the TinySA.
Okay.
And that can cause problems. And then see what you get. If the radio looks clean with those settings, honestly, you're probably fine. It's probably a clean radio at that point.
Mark, thanks a lot for hopping on. Is there anything you kind of want to, your final ideas or thoughts here?
I'm not a test expert. I enjoy testing
Nor
things. I enjoy learning, right? So when I started seeing some things I didn't understand with my TinySA, I did what I think hams should do. I engaged the community. I asked my Elmers and the people in the local club, how do I understand this better? How do we make it reproducible? And what can I learn from this process? By going out and testing the radio on multiple different pieces of equipment, we were able to find reproducible ways where multiple people with multiple test sets could produce the same result. And I think that's really what anybody who cares about spurious emissions testing should be trying to do, is not how do you do it at home by yourself with one TinySA, but how do you make sure that your measurements are reproducible across the community?
Yeah, it helps too that once you have multiple kind of inputs, if you will, or testing capabilities, that you can refine how you use tools like the TinySA to get more reliable and more consistent results. And I think we found that through, help with Doug and talking to Steve and using different equipment has helped a ton. So yeah, I agree with you completely.
Well, thanks for the chance to be on here and talk about this. This has been a fun learning experience.
I've learned a ton. I'm telling you what, I've learned a ton from all of this, and getting to talk and spend time with Doug has been amazing. So again, thank you for opening the doors for a lot of that, because I know he's a member of our club, but still, you're like, hey, this is a really good opportunity to go play with cool equipment, and so I appreciate that. Thank you.
It is indeed. All right. Well, Orbu and I say thank you.
All right. Thank you, guys. I appreciate you. Now, Josh, you asked, you want to see a demonstration of how to test for these non-linear products. Well, start your TinySA, go to Measure, turn on Harmonic. I'm going to put 146.52 because this is where I use all my radios, guys. I'm a simplex user. I'm on 2 meter simplex. And the span is always going to be 100K, okay? Now, from here, we're going to go to Level. And we need to account for how much attenuation we have. So we have the 50 dB external, and I've added a 6 dB pad, as they call it. So I'm going to say 56 negative X1. Now, it's perfectly fine to leave automatic attenuation on at this point, and just to get a start of the measurement. So let's capture something here. And this green line, you're going to have to let this go multiple times. It's scaling at the bottom, right? And you're going to see right now we're at 0 attenuation, and it's going to start to add attenuation as we go. It's probably going to top out at, 10, 14 dB, something like that. Now it's at 13. Okay, it's kind of calmed down, so I'm going to tap the screen. I'm going to go back again, and I'm going to hit pause. So I can let go. Now we're capturing the data here. I would, at this point, log all this data, right? So your 1T is the fundamental. This is the radio. This is where it's transmitting. It says that, 146.52. Then capture all of these, and you can capture them as deltas of the 1T or second harmonic, third, down the line. As part of Eric's website, he mentions for a spur-free dynamic range, we can then change the attenuation values to see if any of these spurs drop in a nonlinear fashion. We've got this fundamental here, and then we've got a second, a third, and a fourth. And see how it's kind of a sweep? That's more or less what you would sometimes expect to see with a harmonics test. Not all the time, but, kind of what you'd expect. Then you get down here, 5, 6, 7, 8, and that 8. That's scary way down there. So let's change the attenuation. You can do that by just tapping the attenuation right there. Brings it up. Let's set it to 20 dB. And we'll take pause off. And we'll do it again. So it should drop out. It's dropped out. And let's give it another go. Okay, we'll pause here. Now, same thing, capture that data. Now, what you might find is that your fundamental frequency is going to be about the same, and your second is also probably going to be matching. Meaning, what the SA is doing here is it's attenuating the incoming signal, but then it's providing gain on the other side. So you're not going to see a variation between those values. They should remain the same. The other values that vary, probably in a nonlinear order, meaning they're not following a linear graduation, that's likely an indication that it's not a real value. Again, a nonlinear byproduct of something that's going on in the TinySA, not coming from the radio, which means you should probably omit it or at least figure out what's going on there before you say, hey, this eighth, for instance, if it was above a certain dB, is violating the FCC rules. I'm talking to Steve Uckerman, N2JXL. So, Steve, give me a quick little background on kind of who you are, what you do, why we're talking to you today. Why would we look to you for possible answers here?
Well, I've spent the past 40 years of my professional career in the design, construction, consultation of high power RF systems, from commercial to broadcast to military applications. This has been a lifelong passion. It's not only my job, but it's also my hobby.
All right, so Steve, one of the big questions is, why is the internal attenuation for the TinySA so important if we're going to try and do like a spurious emissions test?
Well, one of the things that it does is it prevents you from overdriving the first mixer or any of the front end stage of the spectrum analyzer, either driving into compression or becoming nonlinear. An example of this is right now I have a fairly I have a signal close to the input level of, or maximum input level of the device, just as an example. And right now, if I go ahead and turn on the internal gain attenuation, you'll watch those spurs drop. So, and they'll drop with a greater amplitude than the fundamental did.
Meaning they're non-linear products.
They're non-linear.
They're not from the transmitting frequency. That's not a part of your frequency generator. It's something else. It's not something that's under test, which is the point, right?
Correct. And it could be mistaken. And so, for instance, if I drop the gain, or I'm sorry, if I drop the amplitude of the signal in question, here, we'll drop that. You'll notice that while I've dropped this by, say, 5 or so dB, these have all but gone away, and those were greater than at least 5 dB above the noise floor.
So I think you watched the Smoking Apes video, and he had his nice fundamental at the one spot, the one marker, and then there's not a lot in the second, third, or fourth harmonic, and then he got a bunch of products on the 5th, 6th, 7th, even the 8th. I can't remember exactly. I'll overlay on the screen right now so people can view what we're talking about. To me, when I have a fundamental, frequency that I'm transmitting on, I expect to see harmonics in that 2nd, 3rd, 4th, possibly like into 5th. But when you're getting all the high bits, if you will, in the 7th, the 5th, 6th, 7th, 8th, that makes me think that there's probably something else going on. Is that like a safe assumption, or what does that mean?
That's interesting. I saw that too. It's hard for me. It's hard for me to, as an engineer, it's just, I would see that and say that warrants a second look, maybe even a third, because it's unusual to see harmonics that high up at those power levels. So one thing you can do is if you want to eliminate the possibility of harmonics, or if you want to see if it's truly coming out of your radio, you can use something like, for instance, here's an example. This is just a regular 2-meter 440 diplexer. If you terminate the UHF side and just use the VHF side, this basically will roll everything off above, say, 180 megahertz. And so you could basically eliminate, if it's from the radio, if it's truly from the radio, you should eliminate all the harmonic content out of the radio. It's a pretty valid little test to use that as a low pass filter and see if that actually cleans it up. And if it does, it may actually be something coming out of the receiver, or out of the radio, out of the transmitter.
Sure.
So that's one way to validate that. The other thing you can do is if you're curious about how they behave, if it's a mixed product or something that may not be happening in the transmitter, is you can adjust the power, and usually by stepping the power down, if the harmonics don't move at the same speed as the fundamental. So for instance, if I crank in 1 dB or 5 dB or 10 dB, if the harmonics don't back off at the same amount or at the same rate, then there's something nonlinear happening. And then you have to go look and find out whether that's something that's truly happening in the spectrum analyzer or in your unit that you're using to measure, or in your device under test. And sometimes that's a hard one to eliminate.
Yeah, it was interesting. At the end of the video, he put the antenna back on the Baofeng Mini, and he had another kind of a handheld spectrum analyzer next to it, and he transmitted, and he showed on this other analyzer over the air that he was getting that fifth harmonic spur, which looking at yours around the same space, is like 700 megahertz, somewhere around that space. So is that also just a byproduct of, hey, I've got my handheld at 5 watts, less than a foot away from the antenna on this SA, or something along those lines, and I'm transmitting into it? Can I create the same non-linear artifacts, if you will, by just doing that, whether it's over the air or on coax or whatever?
Well, so if it's adding attenuation or loss is not going, like he mentioned in his video, he's 100% correct. Adding attenuation or loss is not going to create additional harmonics. It will attenuate them, and it should attenuate them correctly. When he had his little the receiver, the little SpecAn handheld unit sitting next to the transmitter, it's 5 watts sitting in front of a device with an X number of dB dynamic range, and I'd have no idea how badly or poorly it was overdriving that unit. That the poor front end on that was probably, the AGC was just crawling out of the case.
Well, let's assume he dropped it down to like 1 watt, because I think that's the lower end of the Baofeng Mini. That's still really close to.
It's still really hot. Yeah, exactly. So it said 65 dB, minus 65 dB. It's a relative measurement to what? So can you hear it? Possibly. The inverse square law, you walk a few feet away, is it still there? I don't know. Again, that's not a measurement technique we would use. It's something that you might say anecdotally, you might use anecdotally, or it's a point where if I hear this, I'm 10 feet from my transmitter and I'm hearing the fourth harmonic, maybe I should go retune or see if there's something up or something's not right. Then I'd go and actually measure the device. It's a good data point. It's nothing I would ever measure on. Being that close to the spectrum analyzer with that much power, it's just not a valid test.
So this is the Agilent E5062A ENA. It's basically a vector network analyzer, or VNA. And what we're going to do is characterize the attenuator setup. And we have 2 attenuators. One is an HP 8494B, and that is a 1 dB per step attenuator out to 12 dB. And the other one is a JW Industries 50 dB attenuator, or 60 dB attenuator, and I believe that's in 10 dB steps. And in series, this allows us to make any combination out to about 70 dB or so of attenuation. So when we need to adjust the attenuation in the measurement setup, we want to make sure that the attenuators themselves are working correctly, that the step sizes are what they are within a half a dB or 1 dB, and that we don't get any additional losses or gain, and that it's flat over the frequencies of interest. So here we've got our fundamental on marker number 1, and we've got the harmonics on 2, 3, 4, 5, and 6, and the frequencies are listed here. This end of the display here is out to 1.5 gig. We could go out to 3. The attenuators are good out to 18. They're flat from DC to 18, and what we're going to do is just step through these very quickly and just make sure that the step sizes are correct. So on the 1 dB per, I'll just go ahead and move these down. There's a little bit of averaging, but we're just looking for consistency in the attenuator step size, and these are behaving as calibrated, so we should be able to go out to about 12 dB, 10, 11, 12. So there's 12 dB. And you notice that as further we get out, there's a little bit of roll off. So about a half dB or so of additional attenuation, but we're well within spec for this particular attenuator. So I'm going to go ahead and crank that back to 0. I'm going to go ahead and adjust this in 10 dB steps. As you can see, as expected, smoothly, we're able to jump in 10 dB steps. So if I wanted to, I could make any combination. There's 40, and if I add 1, we should be able to go to 41, 42, 43, etc. So when I dial in 43 dB of attenuation, I know exactly what it is. The reason why this is critical is when we go ahead and make the measurement, one of the things that we have to account for is all the attenuation in the system to set the correct conducted emissions level. It's kind of critical in the test setup to make sure that, at least procedurally, that we have the correct attenuation and we know what we're looking at. So we're at the spectrum analyzer. This is an HP 8590L. This instrument will cover 9 kilohertz to 1.8 gigahertz, and it's perfectly fine for this application. We're going to be looking at the second, third, fourth, fifth, possibly sixth harmonic. So that's roughly 291 megahertz out through, say, 873 megahertz. Let's see if we see anything there. First thing we're going to do is we're going to find a comfortable operating level for the attenuator setup so that we can set the level from the HT, the energy out of the coupler, into the spectrum analyzer. And we want to make sure that the analyzer is not in compression. We are not generating any interesting harmonics or artifacts in the instrument itself. We don't want to measure the analyzer. We want to measure our device under test. So make sure that we've got everything clean. This analyzer actually has the ability to take a watt in, so this is a pretty beefy front end. And we're going to try and get as close as we can to the 0 dB reference line. The reason why is the dynamic range on this instrument is kind of limited, but it should be fine for at least seeing the conducted spurious emission limit at minus 16 dBm. Let's talk about that real quick for a minute. The rule, CFR 47, part 97.307, subpart E, says that any spurious emission from 30 to 225 megahertz must be at least 60 dB down from the mean power of the fundamental. It's important, the use of the word mean is important, and it means something. It means that we're looking at an average power level. For transmitters having a mean power of 25 watts or less, the mean power of any spurious emission supplied to the antenna transmission line, that's important, to the antenna transmission line. This is not a field strength measurement, this is not a radiated measurement, this is not measured at X number of feet, it's not measured at a distance. This is into the antenna transmission line, must not exceed 25 microwatts. 25 microwatts. That's roughly 0.025 milliwatts. So that's down there. It's a pretty good limit. So when you do the math, 25 microwatts is essentially minus 16 dBm. So for any power level from low power to 25 watts, you cannot have a spurious emission that exceeds minus 16 dBm at the input of the transmission line. At the same time, it says, and be at least 40 dB below the mean power of the fundamental. So we have to be at least 40 dBc to be legal. So we have to meet both of those requirements. There's an and in there, so it's important. The words count. We'll go ahead and set our frequency at 145.5. That's where I'm going to be making the measurements today. We'll set a span of roughly 5 megahertz. We'll put the marker on, and let's go ahead and let's turn the radio on. Frequency mode. Here we go. Now let's go ahead and transmit. Now remember, I'm into a 50 ohm load, so we're going to go ahead and transmit. And there's our carrier. So we'll go ahead and hit peak search, and that's our carrier. So what we're going to do is I'm going to adjust the attenuator so that we get that peak as close as we can to the 0 dB reference line, and then make sure that we are not overdriving the front end of the spec end by changing the attenuation in 1 dB increments or 10 dB increments, and making sure that everything follows at the same speed. So let's go ahead and key up. I'm going to drop the carrier in between changing the attenuator adjustments, because I don't want to accidentally do that while I'm applying power and actually accidentally have the attenuator fall in a spot that doesn't have any attenuation. So -1 is perfectly fine. So I'm going to go ahead and change this by 1 dB. And it follows right along. So if I crank in 1 dB, I am getting 1 dB changes. That is fine. Let's go ahead and set up to do a measurement. I'm going to set the sweep. Let's set this at 138 megahertz, and we'll go ahead and set the stop at, say, 1.7 gigahertz. And if you notice, the noise floor came up, and that's to be expected. One of the things that we can do is, if you notice, the resolution bandwidth is set at 3 megahertz. It's very, very wide. One of the things we can do is if we change the resolution bandwidth, this is the filter to the mixer, the IF of the instrument. If we narrow that up, we reduce the amount of noise that we're introducing into the instrument to be measured. So let's go ahead and we'll change the resolution bandwidth down to, let's go down to about 30 kilohertz. We can go down to 10, so the sweep gets a little painful. So I think 30 for now is a good trade-off. And we'll also check the video bandwidth is down to 30. So let's see, we can also go to 10 kilohertz there. So I think that's a good starting place. What I'm going to do is I'm going to put this in single sweep. And what this allows me to do is to just run the sweep, and then I can unkey and I can go back with the marker, and we can scrub around with the marker and find all the peaks that we want to, that may be of interest in this test. So the limit, this conducted spurious emission limit, is -16 dBm. And we can't just set a reference line at -16 dBm. The energy that we're delivering to the spectrum analyzer also passes through a 20 dB mean coupling factor, a -20 dB mean coupling factor, and roughly here 17 dB of attenuation in the attenuators. What we have to do is we have to account for that 37 dB of attenuation on top of the 16 dB that is the limit. So that brings us to a conducted spurious emission limit of -53 dBm as read on the spectrum analyzer. So again, while the limit's 16 dBm at the output of the antenna, we have to translate that through all this loss to the correct reading and scale it correctly so that we are looking at the correct level on the spectrum analyzer. Otherwise, we're comparing coffee cups to apples, and that's not a good comparison. Let's go ahead and I'm going to key up, and I'm going to go ahead and hit single sweep. Okay, and I can unkey. We notice that there is some stuff that we see on the display. And what I'm going to do is I'm going to take the marker, and the first thing we should do is make sure that we meet the -40 dBc, because that's the less strict of the two requirements. So I'm going to go to peak, and you can see way on the left-hand side is our carrier. Now the frequency counter is going to round to whatever it thinks it is. It's not -154. I can tell you that that is definitely -144. So that's to be expected. But what we are looking at is the level. So I'm going to go ahead and do a marker delta, and I'm going to go ahead and find the next peak right, and that has a level of, what are we reading there? -59.55. Let's just make sure. -59.55. Good. Okay, we have to meet at least -40 dBc, and as you can see, that is definitely more than 40 dB removed from the carrier. So we definitely meet the -40 dBc, and by just by approximation here, you can just by looking at the display here, we can also assume that these are all well below that as well, since they do not exceed the amplitude of that second harmonic. And in this particular radio, the second harmonics, the even order harmonics, seem to be a little bit hotter than the odd order harmonics. So this is our, let's see, 574. So this is our fourth harmonic, I believe, and we'll keep an eye on that one as well. But that's definitely definitely meets and exceeds the minus 40 dBc requirement. I'm going to go ahead and take the marker, go back to marker normal, and now we're going to make an absolute measurement. Since we know the losses in our system, we know how much power we should be seeing or measuring on the display, we can read this directly. Let's go ahead and do peak search, and we'll do a next write minus 60. That's awfully close, minus 60.98. That is well below the 53 dB conducted spurious emission limit. So the minus 53 is our new minus 16 dBm, and we meet that. It's perfectly fine. And we can also see through observation here that the second, and I believe this is the third, is that the third? I think that's the third, yeah, the third. And this guy should be, what is it, 587, so that's the fourth, and 727, which is the fifth. Yeah, so these all make it. These all make it handily. And there is a little bit of energy out here at each, so that is the sixth harmonic. So there's some stuff out there. We make it. This passes. This is as a standard test using a standard test methodology and into a 50 ohm load. This HT absolutely makes it. There's no question about it. In fact, we'll just to make sure that it's repeatable, I'm going to go ahead and key the transmitter and hit single sweep, and we'll just make sure nothing's really changed here. And this all looks very similar. There's no major change. So that's good. So our test is repeatable. We're getting repeatable results. The battery is at full power, and this is the expected performance of this particular transmitter into a 50 ohm load. And that's a conductive spurious measurement. So the spectral purity on this, although it's not the cleanest radio I've seen, it is definitely it definitely meets or exceeds 97.307. Just for giggles, let's go ahead and change something. So what we'll do is we're going to do something a little non-standard. I'm going to take the output off of the directional coupler, and I'm going to put the antenna that comes with the radio on the directional coupler. So essentially the radio, instead of seeing a 50 ohm load, is going to actually see an antenna. Now, again, this is kind of non-standard. This is an uncontrolled environment. I am radiating 5 watts of energy into the shop or into the lab here. Everything's well shielded. I don't anticipate that this would be a radiated problem. I'm probably 3 feet away between the antenna and the spectrum analyzer. I know that this particular analyzer is shielded, but it's just, this isn't the normal test. But let's just see what happens when we put the antenna on. So I'm going to go ahead and key the transmitter, and let's see what happens. If you notice, this looks a little different. We've changed the output impedance of the load. We've changed the impedance of the load that the transmitter is seeing. So let's go ahead and measure that. So marker, let's go back to our peak search. We'll go to marker delta, and we need to beat minus 40. So we definitely beat there. How about here? We do. We meet that. So with that antenna on, we meet the minus 40 requirement. That's minus 40 dBc requirement. Let's go ahead and change the marker back. Now, I have not changed the gain. I have not changed anything else. That's one of the reasons why I'm using the directional coupler, is that the measurement setup has not changed. This is still all consistent. We haven't changed anything in the actual sample port itself. Just the termination to the radio, which is now an antenna. So I'm going to set the marker back to marker normal, and let's go ahead and measure this. So again, nothing's changed here. We still have to beat, what did we say here? Minus 53. So minus 60, we're good there. We definitely meet here. And if you notice, these are different. Minus 65, and we do, let's see here, minus 57. Within margin of error, we do meet the minus 53 or minus 16 dBm conductive spurious emission limit with that antenna. Are they higher? Absolutely. Is the Output of this radio, very well controlled, depending on the impedance it sees. Maybe not. But again, this is not how we would do the test in a lab. This is an empirical test at this point. It's a good data point, but with that particular impedance, clearly we can see that something has changed. Something in the nonlinear elements of the output device itself, in that nonlinear transition region, has decided that it's going to generate some products that are definitely spurious, but we don't see anything much past that. There's definitely not any energy there. Let's really change it up and put a really messed up antenna on this, and I can't imagine that this would be something that you would want to run, but just for the giggles, I can go ahead and put a very odd load on this. And this is not what I would recommend, but let's go ahead and I will key up now and we will hit single sweep. This is a very different impedance. Okay, so it didn't change appreciably. Let's go ahead and marker normal will go to our peak over there. We'll hit marker delta, and let's make sure that we hit our minus 40s. And so, yeah, we're still in the minus 60s here. We're still meeting or exceeding the minus 40 dBc. Even there, we do meet it. It is higher. It's a minus 51. It's a minus 51 spur, so it's there, and we'll go ahead and take a look at that in a little bit more detail. Let's go ahead and hit the marker, and let's look at the absolute amplitude of that. This is the one I'm concerned about, and yeah, with this, so within the margin of error, we may or may not. We're right on the hairy line, so this is something that we would need to go back and actually do a full calibration. We would need to characterize all the cabling, all the gains and losses in the system, and see if we make it. This is marginal, but again, it's into an antenna or a termination. It's into a load that is not standard. It's not something you would normally operate on, and we're stressing the output of the transmitter to operate into that load, and clearly it is capable of generating something that may or may not meet the conducted spurious emission limit. But again, I don't think you'd have that antenna on there for very long. The radio definitely doesn't like it. One thing that we have to be careful of is in the setup itself, if we don't pay attention to doing things repeatably, we can alter the results appreciably. So this is the measurement setup on the bench. We'll walk through this. This is the Baofeng Mini HT here, and we're using an HP 778 dual directional coupler. And what this does is it allows me to take the output of the HT, feed this into the directional coupler, and this is essentially a through pass right to the output port. And then the HT is essentially looking at this termination through the coupler. So right now that port's sitting at 50 ohms resistive, which is our standard termination. What we can also do is we can isolate just the output of the transmitter by using the forward port 20 dB mean coupling port. So since it's a directional coupler, I'm looking at any energy radiated or coming from the HT will find its way through this port at a level of roughly 20 dB down from the input of this input of the coupler. On this particular port, on the forward port here, the 20 dB coupler, I go into a microwave step attenuator. This is good from DC to about 20 gig. This will allow me to increment attenuation in 0 to 70 dB 0 to 70 dB of input of attenuation in 10 dB steps. And then that's in series with an HP 1 dB per step attenuator, and the output of that feeds the spectrum analyzer. So this allows me to adjust safely the energy that we're coupling into the spectrum analyzer without damaging the front end, and setting a correct and comfortable operating range so that we don't overdrive the input of the spectrum analyzer or send it into compression. The reverse port is terminated. One of the things that this directional coupler allows me to do is, while I have this terminated into a standard 50 ohm impedance, a 50 ohm resistive load, what I can do is I can disconnect this without disturbing anything else on the setup, and actually replace this with an impedance of my choice, and have the HT look into, say, an antenna or some other load without disturbing any of the other anything else in the setup, with a fair degree of isolation. So it's a good way to test this. I've already characterized the linearity of the step attenuators over the range of interest. So from about 100 megahertz up to about 2 gigahertz, we've already characterized these, and these are essentially flat. These are both good. I think this step attenuator is good to about 18 gig, and this guy's good to about 20. So we're well within the spec. I think we're only going to look at 130 megahertz through, let's say, 990 megahertz. Directional coupler does have a little bit of ripple, but it's plus or minus 1.3 dBm across the spectrum. So this is good from 100 meg to 2 gigahertz. And at the frequencies that we're expecting harmonics of interest, I've gone ahead and written down what that loss is from input to the forward 20 dB coupling port. Okay, I just wanted to switch over to handheld for a minute, and just I want to introduce a duplexer on the input of our test setup. And the reason why is the duplexer will attenuate on the VHF side everything above 180, 190 megahertz significantly. It'll roll things off very, very quickly, so that by the time I get to the second harmonic at 291 megahertz, I'm almost 50 plus dB down. So the stop band attenuation in this is fairly high. So in addition to the attenuator and directional coupler loss, we can include the stop band loss. So it's 50 plus the 37. It can be significant. Even with the goofy load, we still have that stubby antenna. So let's go ahead and go back to the display. I'll key up and let's see what this looks like now. So I'm keyed. I'm going to go ahead and hit single sweep. Again, same parameters, same everything. Resolution, bandwidth, span, gain. Nothing's really changed in the test setup except for the inclusion of a duplexer. If I go ahead and do a peak search, there's our carrier, and it's our fundamental over there. And as we go up here, there's nothing there. I mean, it's just gone. The only thing that was maybe of question, and this is going out to 1.7 gigahertz, is our third harmonic. I think it's our third harmonic, and that's just tiny. That's way down there. So the duplexer, because the stop band attenuation is so great, this basically acts like a low pass filter, and everything below 180, 190 megahertz has only got about a dB or so of attenuation. Yet there's almost 50 plus dB of attenuation in the duplexer that we add to that 37. So it's gone. And so that kind of tells me that the artifacts that we were seeing, the spurs, are definitely coming from the radio. And again, that's under a non-ideal situation. It's a non-ideal load. It's definitely an antenna that I wouldn't want to run. The radio is telling me it's not happy. It's very, very warm, and just not going to run that way. But anyways, so that's the measurement, and those are some things that you can do to improve the accuracy and repeatability of your measurement setup.
So Steve, thanks for coming on and helping to kind of guide how we use some of these tools. Is there anything you want to add? Like, since we've been talking about TinySAs, and obviously you've got this bank of equipment and you've had your hands on all kinds of different testing equipment, how should we look at kind of reviews or comparisons of radios when we're talking about the TinySA or devices like it, small little devices?
I think they're very powerful. The TinySA and the nano VNAs and some of these handheld devices are just amazing. For those of us that were weaned on some of the gear of the past 15, 20, 30 years,
Everything behind you, right?
everything behind me, and my roadie on the floor. Oh, I'm so sorry. um, when you go from like a 30, 40, $50,000 instrument that's been condensed down to a little box that costs $200, it's mind boggling how easy now it is to do some of these very complicated measurements so easily, and it makes it so affordable to the masses. The caveat is that unless, it's nuanced. So the measurement, unless you understand the measurement, the procedure, and what the data is telling you, what the instrument's telling you, unless you know how to interpret that, you can make some very wrong assumptions, and some very wrong actions based on data that may or may not be correct. So you have to be very careful with how you do your measurement. You have to understand what the data is telling you, what the instrument is telling you, and you'd be prepared sometimes to just say, oh, I should probably retest that, or maybe my methodology was wrong. This is why test methodology and test procedures are very standard, and they need to be for a reason. It needs to be very repeatable, and that's, repeatable results are the hallmark of good test and measurement.
Well said. Well, thanks again for being on. I appreciate it.
Oh, my pleasure.
And so while the goal of this video is to help, again, educate everybody on how to use the TinySA appropriately, it's also to get back to this fundamental statement that was a part of the title of Abe's video, that the Baofeng Mini is a dirty radio. All of them. There was no implication that it was some, or that maybe he got a bad sample size. He was implying that they're all bad. Unfortunately, I have to fundamentally disagree. Not only did we test against TinySA and found that it was clean, I backed it up with testing with my service monitor and found that it was clean, and then we went to Doug, K6JEY, who is the ARRL technical advisor in metrology and has written the 26th chapter in the ARRL handbook on test equipment and procedures from 1995 to 2014. His home lab employs an array of test equipment, but specifically, we used a very nice spectrum analyzer that had been calibrated with calibrated attenuators against 7 different Baofeng Minis, and we found that they were all spectrally clean insofar as they met the FCC guidelines on what would be a violation of the rules for spurious transmitters. I have an open invitation to Smoking Ape, as it was when we first reviewed these radios, for him to send me one or both of his radios, and I will go to Doug's house. We will test them. We will see if they're clean or not. It's still open. I would love to do that. But truly, honestly, if we're going to get out here and get in front of these cameras, and we are going to try and tell people based off of measured data, not feelings, right? Like, I've got tons of feelings about radios, and I tell you that. I'm editorializing, right? But when I come out here and I test using a measurement tool, we need, collectively, all of us, to be as accurate as possible. And if we're not accurate, then everything we've done in the past using that same methodology is questionable. And I'd go so far as to say we possibly need to go back and re-review some of those radios if we didn't use the right methodology, because we have erroneously given people failing grades on radios. We shouldn't be doing that. We should hold ourselves to a higher level. If there are questions and problems where we don't understand something, or guidance from the community is saying, hey, I think you might have not did this test correctly, then we should look into that collectively. I'm saying we, yes, because I've been in the situation where I've had to go back and make changes, pull videos down, edit them, retest, repost them. That is the right thing to do. That should be the thing we do. As always, these tests, it's oftentimes better to get multiple tools against these different radios, multiple capabilities of measuring whether there's spurious emissions or not. But we have to keep in mind, too, that a lot of times some of these tests are coming down to us using a TinySA, which in itself is a cheap measurement device. There is going to be variations in there, and unfortunately, there are internal spurs that get into some of these data sets, and we need to do what we can to suppress that data from being a part of the actual data set that we're looking for, which is that of the radio we're testing. I hope all of that was clear. If it's not clear, post in the comments below, and I will work through that to the best of my ability. And when I can't do it myself, I will call in people who know more than me, that are more educated, that work in this space professionally, that can definitely provide a better answer. I am Josh, KI6NAZ. Thanks so much for watching. I will talk to you later. 73.